This picture shows the geometry of the way we would set up the lab in a classroom, and a laser shines on a single slit or a double slit, producing an interference pattern. So usually we put a screen a distance L away and look at pattern of a bright spot on the screen. As shown in this figure, let's use L to denote the distance from the double slit to the screen, and YM to denote the distance from the central bright spot on the screen to the M's bright spot. So for instance, Y4 is the distance from the center of the pattern to one of the M4 bright spots on the screen. If the angle is small, say 10 degrees or less, we can use the approximation. Sine theta is approximately equal to tangent theta. And using this assumption, we're going to derive an expression for Ym in terms of d, m, lambda, and L. So we have two equations to work with here. One for sine theta from above, and one for tangent theta from the geometry of the right-angled triangles. So the small angle approximation enables us to set these two equations equal to each other. Doing that and solving for y gives Ym is equal to m lambda L over d. So the distance from the center of the pattern to the M's bright spot. So the equation governing diffraction from a single slit of a width A is this one, which predicts where the interference minima are in the pattern. So the destructive interference happens when A sine theta is equal to m lambda. You need to figure out the width A of the single slit, and you can do this with any of the wavelengths. So here I'm gonna show you one example using the red laser. So here y is the projected distance away from the center, and L is the distance to the screen. M is the order number, just tells you which minimum you are looking at. So M equals 1 being the first minimum from center. From the geometry shown in the picture in the introduction, we also have tangent theta is equal to y over L. By equating these two values, y over L equals m lambda over A, in which lambda is the wavelength of the incident light, A is the width of the slit. You can find out A. So your calculated slit width may not be exactly the same as the answers, but choose the closest answer as you could. The double slit consists of two slits of equal width A, separated by distance d. So the pattern shows features of the first single slit pattern and the interference pattern from two sources. So in addition to the single slit equation above, we also need the equations that predicts the angles at which the interference maxima, the peaks and the minima, the zeros are in the pattern. So the constructive interference happens when d sine theta is equal to m lambda, and destructive interference happens when d sine theta equals half integrals of lambda. So first, you need to figure out the width A of each slit. So to find the slit width, you're going to look at the overall envelope that the peaks are inside of, and it should remind you of the pattern you saw in part 1. So just as what you did in part 1, you're going to choose the appropriate values for M, X, and L. So for solving the single slit width A, we are going to look at the gray line here. So let's take the violet of laser as an example. So we set up the equation m lambda over A equals y over L, and we choose the first minimum, and the distance from the center to the first minimum is 3.3 centimeters, and L is the distance to the screen. And so we solve for the equation, and we can solve for the slit width A. Next, you are going to determine the distance between the two slits of the double slit, so the distance D. Now you are going to look at the set of peaks and troughs inside the single slit envelope. So this time we are using the equation d sine theta equals m lambda, where the constructive interference happens. So we're going to look at the first constructive interference, the first peak, m equals 1, and lambda is the wavelength of the violet laser, 400 nanometers, and the distance from the center of the pattern is y equals 1 centimeters, L is the distance to the screen, 1.12 meters, so we can solve for the D. Now you know the slit width A and the distance between the slits D, and now you're going to use one or both of these to determine the unknown wavelengths. So I'm going to give you an example using the two slits interference results. So because m lambda over D is equal to y over L, and we're using the first order peak, first order maximum from the interference patterns. So, and lambda is unknown. The D is what you got from the previous part, and y is the distance from the center to the first maximum. L is the distance to the screen, so we can solve for lambda. So let's set up the geometry of the diffraction problem. Then we will play with the math a little bit. And so the grating is described by n, given in lines per millimeter. It's the number of slits per millimeter. The value we need is d, which is 1 over n. So d is the slit spacing. So the slit spacing d is in millimeters. W is the slit width. Lambda is the wavelength of the light. So m is the maxima counter. So if m equals 1 is the first order maximum. And theta is the angle you're going to measure. And angle theta won't be the same for each grating. So in this part, you are going to explore the interference from a diffraction grating. So a grating is like a comb. There's a whole bunch of equally spaced openings, and that will result in a very defined interference pattern, and you're going to watch the videos to learn more about it. So in part 4, you're going to observe the diffraction of laser light of multiple wavelengths. You're going to compare the effects of different grating slit spacings, And you're going to measure the angle of a diffracted light and use it to calculate the wavelength of the laser. And you're going to analyze the measurement techniques and apply the diffraction geometry to an unknown grating and determine its slit spacing. So the second video allows you to control the laser wavelengths and the diffraction grid spacings. So for this exercise, you should choose the wavelengths and measure the diffraction using the same laser, but testing the array of different gratings. So you gotta use the protractor to measure the angle of the first order maximum. So when you are placing the protractor, so make sure that the center of the protractor sits exactly where the laser branches out. So as you can see, you can place the center of the protractor at the diffraction grating. And you can also resize the protractor by dragging the corners and rotate the protractor by grabbing the edges. So to get the correct protractor reading, you may notice that the top of the arc shows degrees from 0 degrees to 90 degrees to the bottom. And the smallest tick mark along the edge of the protractor represent 1 degree intervals. So if we want to measure the angle for the first order maxima for the green laser light, we can see that the degrees measures 32 degrees. So around 32 degrees. So you're going to show your work for the calculated angles and compare the calculated angles with your measured angles in the video. And you're going to use the double slit equation to calculate the angle of the first order maximum. So d sine theta equals m lambda, and theta is arc sine m lambda over d. So we're using first order, so m equals 1. Lambda is the wavelength of the incident light. In this case, it's 405 nanometers, the violet light. And d is the line spacing. So it's basically 1 over n. d is 1 over n. So it's 1 over 1,000 millimeters. And that's equal to 23.9 degrees in this case. One thing to mention, worth mentioning, is that if you are given a number of slits per millimeter on the grating, like n equals 1,000 lines per millimeter, and you're gonna calculate the line spacing d. So d is basically 1 over n. So 1 over 1,000 lines per millimeter equals 1 over 1,000 millimeters. So if you convert the unit conversion from millimeters to nanometers, you can get the line spacing, the grating spacing to be 10 to the third nanometers for 1,000 lines per millimeter. For part 4b, you're going to determine the grating spacing for a grating with unknown line spacings. So you're going to calculate the line spacing for this diffraction grating using each possible wavelength, then average your values and report the line spacings. So you're going to use the equation d sine theta equals m lambda, and lambda is the wavelength of the incident light, 405 nanometers. We're still using the first order maximum, m equals 1. So theta is the angle for the first order maximum, and you're going to plug in the numbers to figure out the d, the line spacing d. and convert the d to n by reversing it. So lastly, you're going to find the distance y for using the expression with the variables lambda, L, and D, and you're going to use the trigonometry to relate L, D, and Y, and then use the small angle approximation. So the sine theta equals tangent theta. So you're going to use the equation m lambda over D equals Y over L. So Y is equal to m lambda L over D. And the line spacing D is what you got from the previous part. And L is the distance, 100 millimeters. M is 1, the first order maximum. And so you can calculate Y.